Alright, silly people, here's the situation. We are just going to be checking the uncertainty principle for this wave function, which was the result of solving the Schrodinger equation in a delta function potential. Um, so it's pretty weird, and its problem's kind of interesting because it is just it's really a test of how well you can work with crazy distribution functions like the Heaviside function and the Dirac delta. So first of all, the expectation value of x, you're going to take the square modulus of the wave function and multiply it by x, integrate over x. This is 0, and I'm just going to argue that because of symmetry, because the e to the absolute value of x is actually an even function uh, around x equals 0, but then x isn't, so it's an even times an odd, so it's an integral of an odd function, so it's 0. So we can move on from that. And also we do get the expectation value of p for free from that via Iron-Vest theorem. So pretty awesome. We do need to do x squared though. So similar looking integral, but with x squared in here. And so previously I have been glossing over some mathematical details dealing with the absolute value function. And that's what I'm going to kind of go into right now. So mod x, if you wanted to, you could put it in terms of the Heaviside functions. You have x, theta of x, minus x, theta of minus x, where theta of minus x is just 1 from minus infinity to 0, and then 0 else. So just a reflection of the Heaviside function over the y-axis pretty much. But yeah, because of that, we have to split up the integral here into a couple of different regions, because I'll now expand this here, and that's going to be x theta of x minus x theta of minus x. So theta of x turns on for all positive x. So you get a integral from 0 to infinity of x squared e to the minus 2m alpha x over h bar squared dx. And theta of minus x turns on for all negative x, which means you also get an integral from minus infinity to 0 of x squared e to the, oh my god, e squared e to the minus, or plus actually, 2m alpha x over h bar squared. That's kind of the trick there. But these integrals are now pretty darn easy. For these guys, they are going to show up again. I'm going to make a couple of different little changed variables. I'm going to define a variable u, which is 2m alpha x over h bar squared with a minus sign on it, where du will be minus 2m alpha over h bar squared dx, and so dx will be minus h bar squared over 2m alpha du. And I'm also going to define a variable v, which is a sort of similar thing. Doing this allows us to like deal with this integral in particular because it's really weird. E to the positive stuff is, it kind of looks strange. I don't know. This is actually now plus h bar squared over 2m alpha dv, which is how I'm going to rewrite both of these integrals. Here you'll get a h bar squared over 2m alpha cubed integral from 0 to infinity v squared e to the minus v dv, the way that I've set that up. But then also minus h bar squared over 2m alpha cubed, integral from minus infinity to 0 u squared e to the minus u du. Right. All of that was just so I can get table integrals. So I'm going to move a factor of h bar sixth over 2/3 m alpha thirds out to the front. And I'm also going to flip the sign of the second integral, because this is 3 minus signs, so it's negative. But then when you flip it again to switch the order of the bounds, and both of those integrals are actually 2. So let me simplify this stuff out front. This is going to be h bar fourth over 2/3 m alpha squared. And then that integral is 2 and that integral is 2. So we get 4. So we get h bar 4 over 2 m alpha squared. And if we wanted to get the standard deviation sigma x, it is just going to be h bar squared over root 2 m alpha. Okay. Now we have to do p squared. This is always the most fun part. I'm going to go ahead and expand the definition of momentum, putting a minus h bar squared out front. And rather than expand the exponential in terms of Heaviside functions straight away, we're just going to talk about what the derivatives of these look like. H bar squared, and then here it's x theta x minus x theta minus x dx. So those h bar squareds out front are going to cancel out, so we'll get a minus m alpha. That's not too crazy. Doing the first derivative of this junk. So we are going to get a factor of minus m alpha over h bar squared. But then we have to take the derivative of that funky combination of Heaviside functions. And then you get back your exponent, which I'm just going to write in terms of the absolute value to save space at the moment. Okay. Now, I'm going to move out a minus m alpha over h bar squared as well. So you just get m alpha over h bar all squared. And I'm going to do the derivatives of the Heaviside function stuff. Obviously, you get a theta of x minus theta minus x, just taking the derivatives of the x stuff and leaving the other things undifferentiated. Um, but then you do uh, x times the differentials of the Heaviside functions. So that is going to look like x delta of x uh, minus delta, or no, it's plus x delta of x. Okay, I just made a bold claim there, and I should probably uh, explain that. Since the Heaviside function is 1 from minus infinity to 0 and 0 from onwards, the slope of the Heaviside function at those 3 points is 0, minus infinity, and then 0. So it's a negative delta function. And then we had a minus sign on there, so the minus sign canceled out the minus sign and made it a plus delta function of x. So those do add up. But I am going to cancel them out anyway, because we know that x times delta x is going to be 0, because you're setting x to 0. So don't even look at that. We just get the Heaviside functions after all. So that was a lot. Now we need to do the second derivative, right? And it's going to be dependent on 2m alpha mod x over h bar squared. So I'm just going to go ahead and write that. You are going to get another term which is proportional to m alpha over h bar squared times the squared Heaviside functions. Now you're just taking these and squaring it, but then you also have to take the derivative of the term which involves the Heaviside functions, which end up just being, so we already did these integrals actually, or these derivatives. So both of those derivatives are delta functions. It's just 2 delta x. Okay, this is looking manageable now, but that's gone. This is just dx now. There's supposed to be a dx there and there. I'm terrible. So yeah, I'm going to expand the square of the Heaviside functions actually. This episode is just full of bold claims, but the square of the Heaviside function is just the Heaviside function. Why? Because the square of 1 is 1, and the square of 0 is 0, and the square of infinity is infinity. So you just get that. But then you also get this plus theta of minus x, and that's interesting. But then the theta functions multiplied by each other will be 0, so there's no cross term. We still get this delta x here. Now we'll split up the integrals into a couple different bounds. So we're going to have an integral over, okay, we're going to have a couple integrals proportional to minus m alpha over h bar squared first. But then we're going to have an integral in the positive x with this delta function. So it'll just be it'll be 0 to infinity minus 2 m alpha x over h bar squared dx. And we also get an integral in the minus x region. So this is going to be minus infinity to 0 e to the 2m alpha x over h bar squared dx. Right. And and we get 2 times the integral over all space of just this 2m alpha x over h bar squared times a delta function dx. And I'm going to use the same change of variables that I did before, because both of these integrals we've actually almost already done. But now we'll just have a h bar squared over 2m alpha integral from 0 to infinity e to the minus u du plus plus 0 to infinity also times h bar squared over 2m alpha. And I think the positive x region I actually defined as v, but then this one was u. Right, but then the Kronecker delta integral we can already just do. You get 2, because e to the 0 is 1. So that's funky stuff. Now both of those integrals of the exponentials are just 1. So we get minus m alpha h bar squared h bar squared over 2m alpha times 2 plus 2. This 2 cancels out here. And actually all these terms cancel out, so that just ends up being minus 1. So we get m alpha over h bar all squared 2 minus 1, which is 1. So we get that for the expectation value of momentum. So the uncertainty of momentum will just be m alpha over h bar. And then the uncertainty principal, let me write that explicitly. Because remember, for sigma x, we got h bar squared over root 2 m alpha. And then for this, we got m alpha over h bar. So we do just get h bar over root 2, which is root 2 times h bar over 2, which is certainly greater than h bar over 2. So uncertainty is all cool here. All right.